Hello, ladies and gentlemen. Today, what we're going to do is learn and go over a little bit about graphing motion with a distance versus time graph. And we're going to try to make some differentiation between what we call average velocity and instantaneous velocity. So here, it looks to be a complicated looking graph, and having a graph or motion graph with this many parts is probably something you won't run into. But if we look at each part individually, it'll give us the skills to analyze almost any distance versus time graph that we might run into. So you'll see here we have some body or something or some object in motion, and we're going to start looking at that motion at time 0. Notice in these graphs you're not going to have anything in the second or the third quadrant because we're not going to analyze anything in negative time. Although there was an article I think that just came out, something about somebody proving time travel might be able to happen. I actually didn't read it yet, so don't spoil it for me. But we're going to pretend we're not going to move back, or not going to pretend. We're going to assume we're not moving backwards in time ever. So we're going to move forward in time, which would mean that we have the first quadrant, obviously, and possibly the fourth quadrant. And we're going to go over why that is in a minute. And I did happen to label very key points where the graph changes the kinds of motion. And in a graph that you would get on a problem, this labeling of points probably would not happen, but it's something that you want to be able to identify as you interpret a graph. Wherever the graph kind of changes its look, you want to identify those key points on the graph. So I have points A, B, C, D, E, and F. Point A to B. Firstly, notice we're going to analyze the motion of something, but the time that we start analyzing the motion is 0, but the position is not 0. There's no rule saying that we have to analyze a position from 0, 0. We don't have to start at the origin. So for whatever reason, somebody was observing something moving, an object moving, and when they started looking at that motion and they started the timer, that object was not at the 0 point. It was 2 meters away. One more thing about these graphs. It is assumed that these graphs are only in one dimension, meaning that object can only move along one dimension, backwards and forwards. There is no sideways motion going on here or up and down motion going on here, which is a little ridiculous because things don't typically just move along only straight lines, but for whatever reason, that's what's happening. And this, of course, is just the beginnings of physics, so we have to keep things on a simpler form so that you can process these kinds of I can talk. So you can analyze these things in a simplistic way so that you can do more complicated analysis later. All right, so look. The first second, while somebody's observing this object move, in the first second, it starts at 2 meters, it's still at 2 meters, and remains at 2 meters for that entire second. So on a distant time graph, you see that flat horizontal part of the curve. There's no motion there. None. It's not moving. It hasn't moved. It's still only at 2 meters. When we go from points B to C, we can see, over and from 1 second to 3 seconds, this object moves from 2 meters to from the 2 meter position to the 4 meter position. It is in motion. Also, because this is a nice straight line, we can assume that that motion is nice and consistent and constant. So the object is moving in a nice constant way. It's moving in a nice smooth manner, not a jerky kind of way, not a stop and start kind of way. So we might be asked, well, okay, it's moving. What direction is it moving? Well, it's moving from +2 to +4 in direction. It's It's moving in the positive direction. And I also can see that very clearly because it's a positive slope. Lastly, I may be asked, well, what is the value of the speed? Actually, the velocity of the object between 1 and 3 seconds. Well, if you want to do this, you can employ you can look at it in a couple different ways. But one of the easiest ways is to say, well, look, it goes from here to here. I can put that line, and I know. Wow, having a rough morning. Anyway, I know that at 1 second it's at this position, at 3 seconds it's at this position. I know it's moving nice and constantly, so I can use the formula. Average velocity is delta x over delta t. And if you do that, you can say, all right, well, this goes from, and remember, delta is final minus initial, and time would be final minus initial. So we go 4.0 minus 2.0, and the time is 3.0 minus 1.0. That would be 2.0 over 2.0, and that's 1 meter, well, 1.0 meters per second. That's positive, by the way, and that's important. It is moving in the positive direction. But you'll also notice that this formula is the same as calculating the slope of this straight line. If you look at the slope and you do your, rise over run, well, your rise is the 2 meters. Your run is the 2 seconds. And so the average velocity formula is the slope of straight lines on a distance time graph. So if you just do the slope, 2 over 2, 1. Well, positive 1 because that slope is positive. So finding the slopes off of a distance time graph is effectively finding the average velocity. Now, in this particular case, the average velocity between 1 and 3 seconds happens to also be every instantaneous velocity. Instantaneous velocity is the velocity at any one particular moment in time. If I wanted to know the instantaneous velocity at 2 seconds, how fast, if I were to see that person walking or the object moving, and at 2 seconds just freeze frame it and ask, well, that very instant, how fast were they moving? Now, don't say they're 0 because you freeze frame. That's not what I mean. Okay, so they're moving at 2 seconds. What was their speed at 2 seconds? Not an average between points. Well, if it's nice and consistent motion, isn't it 2 meters a second for every instant? Right? If I'm moving nice in a constant way, every moment, I'm moving at that same speed. So if I have a nice straight line, a nice constant motion, that average velocity is also equal to all the instantaneous velocities along that way. Now, if we analyze the motion from only points C to D, well, we have to ask ourselves what's going on here. Well, we see a nice straight line, and so we understand that's a nice constant motion. But notice what happens with the displacement. We're starting at 4 meters, and we're going to end up down at -4 meters. Well, what does that mean? So the object moved forward, it got to 4 meters, and then suddenly it goes from 4 meters back to 3 meters, back to 2, back to 0, back to -1. Yeah, it's moving backwards. It's moving behind the origin. This is allowed. you're going backwards. You're going behind the starting point. You can do that. That's fine. Now, we know it's going backwards, obviously, by reading and looking at the graph, but we can also see that by the slope. Notice the slope of this line. It's nice and constant motion again. So, this object was over here. It was moving backwards in a nice constant way. The slope is negative. So a negative slope on a distance time graph means the object is moving in reverse direction. Now, the question is, when they start moving direction, do they just move backwards, or did the object actually turn around? It's a silly question. It really doesn't matter. And so, well, what's happening with the velocity during that time frame? Well, again, you can do the average velocity, the average, and you can do x2 minus x1. So we can go x2. Well, x2 is minus 4.0, because we end up down here at point D, minus 4.0, because we started up here. And the time difference would have been from 5.0 to 3.0. And if you do this, you're going to get negative 8.0 over 2.0, so negative 4.0 meters per second. Now, again, if you take the slope, rise over run of this graph. Now, I'm going to, and when I do slope, by the way, you want to make that rise over run, like little triangle, you want to make that as large as possible, right? So I'm going to unfortunately erase this. But you can see that if I do this slope triangle, rise over run, the rise, well, it's 4 to negative 4. That's 8. That's an 8, and that's 2 seconds. Now, some of you might have said, well, can I have done, this triangle in green? Can I have done this triangle in green, the smaller triangle? Can I do that rise over run in here? And the answer is yes, you could have. And if you do that, the rise would be 4. Well, negative 4, you're moving downward. And the run would have been 1. So you get the same answer, negative 4 meters per second. But I'm going to ask you, in finding slopes in general, finding rises over runs, the bigger the triangle making that rise over the run, the better off you're going to be. Just trust me on that. Okay? And again, since you are moving at a nice constant speed, the average, or velocity I should say, the average velocity is going to be equal to every instantaneous velocity, because at every moment you're moving at that same constant, actually we're moving backwards, nice constant velocity. So that negative is important. That negative tells me direction. That's why the velocity, that's the whole purpose of velocity, to tell me not only the value of the motion, but also the direction of that motion. That negative sign tells me the direction.